Postdoc in the research training grant that we have here is sponsored by the NSF. His title is officially Visiting Assistant Professor. And so Andy was an undergrad at Virginia Tech, where he did engineering sciences and applied math, and then he got a Ph.D. in Aerospace Engineering from University of Illinois at Urbana-Champaign. His interests are pretty wide-ranging, but I would say focus on geometric control theory with applications to mechanics, elasticity, robotics, things like that. So we'll be hearing all about that today in the context of thin, deformable objects. Go ahead.
Thank you, Steve. So, like Steve said, I started out at Virginia Tech as an undergrad. And that's where my heart is, kind of the mechanics area. I did engineering mechanics. It's another department that's now been absorbed into something else, just like here. So one of my main focuses is mechanics of elastic structures. After I graduated, I went to University of Illinois, and I was in an experimental robotics lab, which was different. But I never did any experiments. I was like the theory person in the experiments lab.
And Illinois is another place where they don't have mechanics and stuff.
Right.
Anymore, for the same reason.
So there I was a theory guy. Now I come here, I'm in the math department. Now I'm the very applied guy, which I kind of like this better. So from grad school, I picked up an interest in robotics and optimal control theory. Today, I'm just going to focus on mechanics and robotics. I'm not going to talk about optimal control theory, even though optimal control theory kind of underlies a lot of the results that we're going to see today. When I was putting this talk together, I wanted to kind of have a theme of a method that maybe you could take away from this. So I have a collection of problems where scale and variance plays a really key role. So this is something that hopefully maybe we all learn sometime in our academic career. I think I learned it in a junior level fluid dynamics course. So I'm going to apply scale and variance to some problems in robotics and mechanics today. Now, before I do that, there's a story I usually like to tell when I'm giving this talk. And it's about my first encounter with instability. I'm going to be talking about instability a lot today. So this story goes back to when I was in preschool. I was probably 3 or 4 years old. And we played, usually once a week, with these things. I think they're called geoboards. That's what we call them. I don't know if you all have ever seen them before, played with them. So one day, little 4-year-old Andy wanted to make a train of geoboards. So I got a bunch of them out of the cubby, put them side by side. Took a rubber band, put on one, stretched it all the way down to the last one. And it was fine, so I kept going, adding more and more. And I went one too many, and it buckled. And it buckled at one end, and I was standing at the other. It came flying towards me. I was pretty lucky because the nails missed me. But the corner of the board got me right in the crown of the head. There was a lot of blood, and I had 8 stitches. But it was all good. So now, ever since then, I kind of like to keep things stable. That's what we're going to do today. We're going to talk about how you can manipulate a deformable structure, or in this case it would be a discrete structure, while keeping it stable. We're not going to talk about geoboards. We're going to have a canonical example of a deformable object. We're going to talk about an elastic rod. So physically, you can think of this as a wire or a cable that can deform. I'm going to call this a rod. And usually I'm going to color it yellow or gold. So anytime you see something yellow or gold, that's what I'm calling a rod. The ends are held by robotic grippers. So these grippers, I can specify where in space they are. They're both their position and orientation. We're also going to assume that this rod is elastic, which means if I bend it and then let go, it will go back to its original shape. So there's no plastic deformation. So this is the main problem we're going to solve today. If you give me a starting shape and a goal shape of the rod, can I find paths of those blue robotic grippers that cause the rod to deform from the starting shape into the goal shape? As I've stated this now, we could allow for dynamics, vibrations, that kind of stuff. So this would be a control problem for a nonlinear PDE, which seems pretty hard. So we're going to make one assumption. We're going to assume that everything's happening slowly and the rod stays in quasi-static equilibrium. So I'm moving the end slow enough that I can neglect dynamics, I can neglect vibrations, and everything is quasi-static. So on the surface, this problem seems hard for a few reasons. First, this rod is a continuous function. That's how we describe it. So it seems like it should be an infinite dimensional object. So roboticists, when they see this, one of their immediate things they do is they would discretize it into a bunch of little discrete elements, maybe connected by springs, or they would use splines, or some kind of discretization of this thing that's infinite dimensional. The second reason this is hard is that our goal explicitly asks for paths to the grippers. But the grippers really aren't a good set of coordinates for describing the rod. Specifically because you can have multiple shapes in equilibrium for the same gripper placement. Here we have 3 different shapes, all have the same gripper placement. As we're moving the grippers, the rod can become unstable. So the center configuration here is unstable. It's a saddle point of the elastic energy. These two out here are stable. And you could see this as a pitchfork bifurcation. If you had the rod in an S shape, you bring one end down, the middle shape will become unstable and will bifurcate into these 2 symmetric shapes. You could also have saddle node bifurcations where the rod would dynamically jump to some other shape. Finally, the rod could have self-intersections. Here's an equilibrium shape of the rod. This is also unstable, but also this has an intersection with itself right here. So previous approaches to this problem.
Can I ask a little technical question? When you said the hand orientation is fixed, is that 3, the full rotation, or just the orientation of the tangent vector?
All 3. So it's completely fixed.
The twist as well.
Twist and oriented, yes. So 6 degrees of freedom are both fixed at both ends. So previous approaches to this problem, like I said, they would discretize the rod using some maybe finite element discretization or splines, and then they would use continuation to try and figure out what happens when you move the grippers. So you would start here, they would move the gripper a little bit, and then use continuation to find the corresponding minimum energy curve. The stable shape would minimize elastic energy. They would move it a little bit more to continuation to find a new shape, and so on. So you run into problems when you reach those instabilities.
But they did it quasi-statically like these guys.
Quasi-static, right? But they were minimizing elastic energy each time they moved. So let's restate the problem slightly. It's going to be the same problem. We're going to restate it so that it's a little bit more clear what we want. Our original problem asked for paths of the robotic grippers. We said that's not a good way to describe shapes of the rod because there are multiple shapes for gripper placements. So what we're going to ask is find a path of the rod itself. Ignore the grippers. Find a path of the rod from this shape to this shape through the set of equilibrium configurations. So somehow we need to describe that set of all possible equilibrium configurations. And then we need to just figure out how to define paths from one shape to another. So we're looking for a path through the set of equilibrium configurations that are stable and free of self-collisions. So this is the problem we're going to solve. We're going to ignore the grippers, find a path of the rod itself. Once we have that, the grippers just follow the ends of the rod. We can back out what their trajectory should be.
Do you mind a very basic question?
Yes, sure.
Just in case, well, okay. For those of us who don't think about things like this, what's the larger context here?
So an application.
Yeah, like when would you ever want to manipulate something from a start configuration to a final configuration?
Right, so if we're in a factory manipulating wires so they can be installed, they need to be routed around certain objects wherever they're being installed. In surgical situations, if you have a surgical robot that's manipulating suture, maybe it's tying a knot. So manufacturing and medical seem to be the 2 biggest applications.
Beautiful, thank you.
So these are the main results we're going to prove today. that set of equilibrium shapes that are stable and collision-free is not actually infinite dimensional. The interior of that set is a smooth 6-dimensional manifold. Not only that, but it's parameterized by a single global coordinate chart. So it's diffeomorphic to a subset of R6. So we never even have to worry about changing coordinates or coordinate singularities. The other thing we're going to prove is that under a few assumptions on the rod, that set of all stable equilibrium configurations that are collision-free is path connected. So if you give me any two shapes that are stable and collision-free, I can always deform one into the other. And the proof we're going to give of this is constructive. So not only do we have this result, we actually have an algorithm for computing ways to move the grippers that go between any two shapes. So this is one of the main results we're going to work towards today. But we're going to start out a little simpler. I've been showing a 3D rod. We're going to start out with a planar rod. So what we're going to do on this slide is go step by step through and derive a set of equations that describe equilibrium shapes of this planar rod. So here we have a rod that's confined to deform in a plane. The rod I was showing before was deforming in 3D. This one's in a plane. We have our two grippers here at the ends, completely fixing the ends. We're going to use S to denote arc length along the rods. Here S is 0, this increases all the way up to 1. So the length of our rod is 1. We're not losing any generality there, because we can always non-dimensionalize to get a length of 1. We're going to assume that the rod is inextensible. So the length always stays at 1. It can't stretch, it can't compress, it always has a fixed length. We'll also assume the rod is unshearable, so it can only deform through bending. Shear would be something like this. Right, so we're only allowing bending. So along the center line, we're going to define a frame that moves along the center line. One axis of this frame is always going to be tangent to the center line. That direction is going to be called D1. Orthogonal to that is D2. So imagine this frame traveling along the center line. The origin of this frame we're going to call R of S, so that actually defines the curve that's the center line. Since D1 was always tangent to the center line, we have a first equation. The derivative of R with respect to arc length is D1. So whenever we see a dot, that means derivative with respect to arc length S. Now as this frame moves along the rod, it's going to rotate. We can call that rotation rate of this frame U. This is also the bending strain. And from kinematics, we have differential equations for how these two vectors change. D1 tells the axial direction. There's the differential equation for that in terms of D2 and U, rotation rate. There's something similar for D2. Yep.
I didn't get what
R was the center line, so it's the origin of this frame. Right, so here's R at 0, S increases all the way up to R of 1.
But R is the vector, it's the position vector.
Position vector.
It's the position vector along the center line. Right. So now what we're going to do is we're going to take a small piece of this rod, a small segment, and blow it up over here. The portion of the rod that's to the left of this segment is applying some force and some moment to this end of the rod, this end of the segment. The part of the rod that's to the right of this segment is also applying a force and a moment to the segment. This segment is bending a little bit. So if we balance the forces and torques acting on this segment, we get three differential equations for those forces and torques. M is the moment torque. N1 is the axial force. N2 is normal to the axial direction. Now finally, we need one equation that couples these forces and torques and these kinematic variables over here. That's usually called a constitutive equation. For us, we're going to assume that the rod is linearly elastic. So U, the strain, the bending strain, is proportional to the moment. And this constant that it's proportional by is a stiffness parameter. It depends on the geometry of the cross-section and the material of our rod. We've also assumed here that the rod is intrinsically straight. So if we're not applying any force or torque to the rod, its natural shape is straight. Yeah.
I noticed that your two end-twos are pointing in different directions. Is that purposeful, or?
So here, yeah, so this is what we're doing when we're balancing. Here our frame is like this, right? This frame here, if we imagine it going along the rod,
Okay.
it's here. This one's here, right? So the forces need to imagine them balancing.
Okay, so the.
But the piece of the rod that's missing on the left will have the same orientation as that on the end on the right. Those are the rules of the game.
You have to cancel out.
It's called action and reaction. It is.
Super confusing.
So the last thing we need are boundary conditions. We have a set of differential equations. We need some boundary conditions. So we're going to assume that R, the center line position, when S is 0, is at the origin. It's fixed at 0. Those directors, these vectors here, the DIs, this is D1, D2, those are fixed. The EIs are just standard unit vectors. The boundary condition at the other end, at S equals 1, we're going to call that B. So whenever you see B, that means placement of the robotic gripper at the end of the rod. So that's the thing we're going to move. We're going to assume that one end of the rod is fixed, and the other end is the robotic gripper that's going to deform it into our goal shape. So we could derive these same equations based on an energy analysis. The bending strain here, we could use that to define the elastic energy. There's our stiffness parameter. So this is the calculus of variations problem. We write down the Euler-Lagrange equations. We would recover these same equations here. So, all the possible equilibrium shapes that we could have are solutions of this system. How can we parameterize those? We know that B is not a good way to parameterize all the solutions, because if you specify B, there are multiple shapes that satisfy those boundary conditions. What we learn in a differential equations course is that if we specify an initial condition, as long as these equations here satisfy some continuity conditions, then we'll get a unique solution. So instead of specifying the boundary condition for the robotic gripper at the end, what we're going to do is we're going to specify the initial condition for the moment and the two forces. We already have the initial condition for the center line and this moving frame. So to completely find the initial condition, we just need to define the force and the moment at the base of the rod. So if you tell me the values of these three numbers, I can solve this like an initial value problem and get a unique solution. There's one caveat to that. If the shear force and the moment are both 0, I can get non-unique solutions, meaning there are multiple shapes of the rod, or they're the same shape for the rod for different choices of this A parameter. What this corresponds to physically is me pulling on the rod or pushing. So this is the same shape. Here there's no force on it. Here's the compressive force. There's a tension force. So it's different values of this initial condition that produce the same shape. But as long as this condition is true, the shear force and the moment are both not 0, then we get a unique shape. Is there a question?
I was just trying to relate the curve for the center line with the Frenet-Serre formula from differential geometry. Where's the torsion? I'm trying to pick that
We're in the
up.
plane.
Yeah, so here we're in the
Oh, we're on
plane.
the two-dimensional. Thank you.
Yeah. So we'll get to a 3D rod in just a
Yeah,
second.
okay.
Yeah, thanks. So this takes care of our non-uniqueness problem. Rather than specifying boundary conditions, we're going to specify initial conditions. So a continuous path of equilibrium shapes of the rod corresponds to a path in this A space. A1 was the moment. Sorry, A1 was the axial force, A2 was the shear force, A3 was the moment. So this is the space of forces and torques that are acting on the base of the rod. So my initial shape corresponds to some point in this space. My goal shape that I want to get to corresponds to some other point. So if I take any path in here that gets to the point where my goal is, I'll wind up at my goal. Whereas if I was working in the grouper space, I could take a path from the starting group replacements to the goal group replacements, and I might not get to my goal solution. So here's an example. We're going to move along a path. It's not a very good path. I have these little labels here to tell us when we're in self-collision and when the rod is stable or unstable. And no matter what path we take, we'll always get to our goal solution because there's a one-to-one correspondence between points in this space and shapes of the rod. So now we just need to figure out how to avoid instabilities and how to avoid self-collisions. Because halfway through this path here, we were both stable and we had an unstable when we had a collision. So let's talk about how we can avoid instabilities. So an example we've probably all seen is a sphere and computing minimum length curves on a sphere with great circles. If I have a great circle on a sphere that's less than 1/2 of the radius of the sphere, that's minimizing. If it's more, or sorry, 1/2 the circumference. If it's more than 1/2 the circumference, that's not minimizing. What happens is the antipodal points, there's a conjugate point. Conjugate points tell us when something becomes non-minimizing. That same idea can be expanded to more general problems. So here we're using that for the elastic rod. So a shape is a local minimum if it has no conjugate points. The way we find conjugate points is we take the equilibrium equations that we found earlier and we linearize them about a solution. So first we find a solution, then we linearize our equilibrium equations about that solution. If every solution of those linearized equations does not vanish anywhere along the rod, then it's stable. If at some point those linearized solutions do vanish, for example here, then the shape is unstable. This is called a conjugate point. So this is just a test to determine which equilibrium shapes are stable and which ones are unstable.
Seems like the end point, the stability you're interested in has the far end fixed. It looks like you're looking for relations that don't respect that end condition.
Right, so one way to do stability is to look at linearized solutions with both ends fixed. That's an eigenvalue problem. You're looking at the sign of your eigenvalues. Morse theory showed that you can just look at the linearized solution. Anywhere this vanishes in here, that corresponds to an unstable mode. If we kept solving this past the end, and this vanished somewhere, that would correspond to a stable mode. So there's a correspondence between those two things.
So it's as if this plant had that magic point. It's unstable.
Right.
The curve shape is between the two
Isn't this Jacobi?
Traces back to Jacobi for one-dimensional systems. I had to go to the optimal.
You're right.
I had to go to the optimal control literature, Agershep and Sachkov to find a result like
But
this.
it is in Morse's book. You're right. The vector value piece is in Morse's book.
Okay,
It is.
it is, okay. So now, we have a test to determine which shapes are unstable. We could also easily test which shapes are in self-collision. There's tons of collision checkers available that we could use. So we have this A space. There's a one-to-one correspondence between points in here and equilibrium shapes of the rod. Certain regions of this space are off limits. Think of them as obstacles. That obstacle might correspond to an unstable shape, or it might correspond to a shape with a self-collision. So what we need to do is, given 2 points, find a path that avoids those inadmissible regions, obstacles. So here's an example of such a path for the same goal and starting shape we had earlier. So here we're always going to stay stable and we won't have any self-collisions.
care about if you come near an unstable place? Like in an application, you might not want to wind up close to it.
Yeah, that's a good question. So, I'd say yes, you don't want to, it would be a good idea to stay away from instabilities, places that are close to instabilities. But the question is, how do you measure that? What's a good way of measuring how close you are to an instability? So I've seen some work on that, but nothing has really given a definitive answer, I think. So it is a good idea, it's just determining how do you measure how close you are to an instability. Yeah.
Is there anything special about when you pass through the plane corresponding to A2 and A3 being 0? Because you said before that corresponds to non-uniqueness.
Yes, so
Here your path you always go through that.
so there's a few ways to look at, sorry, what was the last thing?
Your path that you were showing has a point on the curve, which is it corresponding? No, not that. Okay, I thought your last one corresponded to it. So you also avoid.
Yeah, we're also avoiding that. So we're planning in that space we call A, which took out that line. And there are a few ways to look at it. One reason is that the map from A space to shape is not smooth at those points. Another way to look at it is that those shapes are statically indeterminate. From a variational perspective, those shapes are abnormal, so we can't test their stability. So what we're going to do is just avoid them altogether. So the main result we can prove from this work is that instead of all stable shapes instead of all equilibrium shapes that are stable and collision-free, the interior of that set is a smooth three-dimensional manifold, and this A serves as a coordinate chart, a global coordinate chart. That's a nice theoretical result. On the more practical side, we can sample configurations by choosing A values that are in some subset of R3. We can check if that shape is stable, and we can check if it has self-collisions. So we have a configuration space, and we have a way to check if the configuration that we pick is admissible. So this is a standard motion planning problem in robotics. We're in a three-dimensional space. It's like this room. Maybe the stable shape, the unstable shapes, and the shapes with collisions correspond to obstacles like the tables. We have to find a path from here to the door. It's a very standard motion planning problem for which there are hundreds of different solution methods. So now let's go to the 3D rod. The setup is very similar. We have a frame that moves along the rod, just like we did in the 2D case, but now this frame has another axis because we're in 3D. I'm going to call this frame Q. And we want to describe the space where Q lives. It's a Lie group called the special Euclidean group. Our elastic energy now has 3 terms. Before we just had 1 term. We have 3 terms now. One of them is the twisting strain. So that's how much this frame twists. The other 2 are bending strains, how much that frame bends as it travels along the rod. I've written the kinematic equations in a nice compact form. We also have boundary conditions. This is saying that the frame at this end is fixed. So this gripper is just staying in place. B, remember, is the thing that we can move. So this is the gripper at this end that we're going to move around to try and deform the rod into a desired shape. So in a similar way we did for the planar rod, we could derive equilibrium equations. We have our kinematic constraints. We have constitutive equations that relate the bending and twisting strains to the moments with some stiffness parameters. And then we have a balance of moments and forces. So again, these are just equilibrium equations that come from balancing equilibrium moments and forces. We also have the same thing with initial conditions. We have an initial condition for Q that fixes this end of the rod. If we specify the initial condition for our moments and forces, we'll get a unique solution. Same thing as in the planar case, but now, since we're in 3D, the moment and force have 3 components each, so we have to specify 6 numbers rather than 3. And now that plane that we have to avoid has this form. So it's where A2, A3, A5, and A6 are all non-zero. So the 2 shear forces and the 2 bending moments are all non-zero. So the shapes that are in this plane have an axial force, either compression or tension, and there's a twist. Those are the abnormal shapes we want to avoid. So just like in the planar case, we can prove a set of all stable and collision-free equilibrium shapes is a smooth six-dimensional manifold parameterized by a single global coordinate chart. So practically, on the practical side, that means we can sample equilibrium shapes by choosing values in some subset of R6. Again, we can check if they're stable and if they're collision-free. So now we've expressed this problem as a very standard motion planning problem, but now in a six-dimensional configuration space. So here's an example of a path we planned. So our starting shape, we're going to deform into our goal shape. So this is always stable and always collision-free.
And this is done all just moving a single arm, so the second arm stays fixed.
Yeah, so this one is staying fixed. So if there are no external forces, which we haven't included yet, I could take this thing and I could rigidly move it around, and the shape would stay the same, right? If I add in gravity, I can't do that. I can only rotate around gravity, move up and down. So there, but when there's no external forces, there's no loss of generality fixing one, just moving the other. So we can extend this in multiple ways. We can allow the rod to be extensible, so it can stretch, it can shear. We could allow the rod to be intrinsically curved or have some non-straight shape. We could add external conservative forces such as gravity. The other thing we can do is have the rod be held by multiple grippers. If we have a very long rod, and if we bend it very much, it's so long it'll become unstable. But if we have multiple grippers along the rod, we can stabilize it. So we can derive similar results in those cases.
What about adding and removing grippers? Like
So-
while you're bending it?
While we're doing it?
Yeah.
Yeah, so what we would have to check then, if I have 3 grippers, say on some segment, I would need to check if I remove this gripper, would this thing still remain stable? So you can think of that intermediate gripper as stabilizing it. We'd have to ask, if I remove it, will it go unstable or not? If it would stay stable, then we could remove it. So what we've done so far is express this problem as a motion planning problem. Now we're going to find a solution that doesn't require any computation. So what we're going to ask is, if you give me any 2 stable and collision-free shapes, and I always deform one into the other. In other words, we're asking, is the set of all stable and collision-free equilibrium shapes path connected? We're going to show that the answer is yes when the rod satisfies the same conditions that we had earlier. It's inextensible, unshearable, intrinsically straight, and there are no external forces. And the way we're going to do that is we're going to use scale invariance. So this is how I typically think about scale invariance. If I have a solution of some system, in this case it's the equations that describe the rod, I can take this solution and dilate it up or down and get a qualitatively similar solution but at a different length scale. So here I've taken this rod and I've dilated it by 2, so I've doubled the size. It's qualitatively the same shape. Here's how we're going to use scale invariance a little bit differently. If I start out with this shape, imagine we cut it in half, remove what's at the end, take what's left, and double its size. So now we're getting 2 qualitatively different shapes but at the same length scale. And I could do this anywhere along the rod. I could start cut off here or here, anywhere, take what's left and dilate it so that this end shape has the same length as the starting shape. So now let's look at what happens to our equilibrium equations when we do that. So let's say we have a rod that has a length of 1. The moments and the forces are given by these, just like we had before, N1, N2, and M. When we cut off a piece of the rod at the end, we're going to call the length that we keep lambda. That corresponds to sticking a lambda to the input of these forces and moment functions. So I'm kind of scaling the input to those functions by lambda. We remove what's at the end, dilate it so the length goes back to 1. When we do that dilation, that corresponds to multiplying the forces by lambda squared and the moment by lambda. So this is kind of like the Buckingham pi theorem, right? This is all just non-dimensionalization. We're looking at how the forces and torques scale as we scale a shape. But we know that there's a one-to-one correspondence between shapes and initial conditions for the moments and forces. So if I pick an initial condition to get this shape, and I scale that initial condition, just like we saw, the forces get scaled by lambda squared, the moment gets scaled by lambda, that corresponds to this scaling procedure we just did, where we cut off a piece and rescale to get a new shape. So now there are two important properties we're going to use based on the scale invariance. So stability and injectivity, by injectivity I mean not having self-collisions, are preserved when we do this scaling procedure with lambda less than 1. So if I take a shape that's stable and collision-free, I cut off part of it, I take that part and rescale it, it's going to stay stable and collision-free. Right? I think collision-free is pretty obvious. If there's no collisions here, I cut off part of it and rescale it, no collisions. Stability also satisfies that.
When you cut down, not if you expand it out, right?
Right, if I expand it out, so if my lambda was greater than 1, that would be something like that.
It would not be necessarily stable.
Right, so here we're letting lambda be less than 1. If I have a shape that's unstable, I can always choose lambda, how much we're keeping, sufficiently small, so that I wind up with a stable shape. I can always cut off enough and then rescale to get something that's stable. Same thing is true with self-collisions. I have a rod with self-collision, I can always cut off enough and rescale to get something that's collision-free. So here's what this gives us. If I take any path in this A space, remember this is the space of initial forces and torques. That path could have instabilities, could have self-collisions, that's fine. I can scale each point on this path back towards the origin. And if I do that enough, every point on this scaled path will be stable and collision-free. Now I can take the endpoints. We're assuming the starting and goal shape are stable and collision-free. So if I scale those back towards the origin, they always stay stable and collision-free. So I started with an arbitrary path, and I constructed a path that is inside the set of stable and collision-free shapes. So we're moving along the first part of our path. You can kind of think of this as a canonical way of unbending the rod. We go along our scaled curve, and then back out to our goal solution. Another nice way to look at this is to watch a rod being cut and then rescaled. So what we're going to see over here is this rod is going to be continuously shortened until we're short enough. And over here we're going to see what happens when we take what's left over here and rescale it. So we're going to start by shortening and rescaling. The rod on the left is going to follow a path that contains instabilities and self-collisions. But we've shortened enough that the rod on the right doesn't contain those. Now we're going to lengthen back into our goal shape.
So on the right side you were plotting that lambda portion, the rescale.
Yeah, exactly. So here, we're taking whatever was colored in over here and rescaling it so that this one always has the same length.
How did you ever think of that?
So, you know Ray Ploutz?
Yes, I do.
He is very careful in his papers about non-dimensionalizing, and that's kind of what led to this. Looking at what happens if you play with L, what happens to the shape, if you play with the length. So we can do the same thing with our 3D rod. Here what I'm going to do, remember we're in 3D, our A space, our configuration space is 6-dimensional. The path we're going to see here corresponds to a straight line in that 6-dimensional space. So we have a starting point and a goal point. The path that we're going to see here is a straight line in that space. What's going to happen is we're going to have a self-collision right there, and that shape is also unstable. And that's fine. I can take any path as long as it stays in my A space. So again, we're going to see a video just like we saw for the planar rod, but now in 3D. On the left, we're going to shorten the rod and rescale on the right. Once we shorten enough, we can follow our path and then lengthen into our goal shape. So the conclusion is that the set of all stable and collision-free equilibrium shapes is path connected. So that's the end of this robotics portion where we're talking about manipulating elastic rods. Let's use this same scale invariance property to solve the mechanics problem. What we're going to look at is the stability of helical rods. So these equations we've been working with in the 3D case were first derived by Kirchhoff, 1859. And one thing he noticed was that configurations can have helical center lines. So here's our model of the rod again. One thing I'm assuming here is that the two bending stiffnesses are the same. So for example, maybe the rod has a circular cross-section, so it doesn't have a preferred direction of bending. If those are the same, I can non-dimensionalize and set them equal to 1. So now I just have one stiffness parameter. So this problem has been looked at before, but there's never been a complete characterization of the stability of all helical shapes. So that's what we're going to try to do.
Those are all force equals 0 shapes?
What do you mean by force equals 0?
Are the helices and the set of initial conditions with the moment of no force is the same?
No, there are moments and forces being applied at the end. We're taking a straight rod and bending it into a helix.
So the initial condition that corresponds to a helix is not a force free?
Right. So these are the initial conditions right here. So an equilibrium shape of the rod with a helical center line with curvature kappa and torsion tau has this initial condition of the moments and forces. So these are the 3 moments, these are the 3 forces. Omega is the twisting rate of that frame that moves along the rod. So here's how kappa and tau relate to the geometry of the helix. And then omega is the twisting rate, and phi or phi is a phase variable. So one thing we can show is that this phase variable doesn't affect stability, which isn't that surprising. It just kind of tells us where along the helix our rod starts. What is kind of surprising is that the stiffness parameter doesn't play any role in stability. You can change the stiffness parameter to make it very high, it's a very stiff rod, or very low, very flimsy rod. It doesn't affect stability. So the only parameters that affect stability are the curvature, the torsion, and this twisting rate. So we can depict the space of all helical equilibria in a 3-dimensional space. So that's what we're going to do here. We have axes of curvature, torsion, and twist. And we're going to use scale invariance to compute the boundary between stable and unstable regions in this space. Here's how we're going to do that. Let's say that I take a ball, or a half ball, because kappa has to be positive, and I pick a point on that half ball. So I pick a kappa, tau, and omega. I'm going to find the helical shape that corresponds to those values of curvature, torsion, and twist. But I'm not going to stop computing those equations at a length of 1. So far we've always talked about rods that have length 1. We're going to let the length be greater if we need to. We're going to keep solving for the shape until we reach the first conjugate point. So the length with that helix becomes unstable. So what these scale invariance arguments show is if I compute the first conjugate point, call that SC, I just scale this point by SC. So here SC was bigger than 1, so this point moves out, away from the origin. If I pick another value of curvature, torsion, and twist, maybe the first conjugate point occurs before 1, I'm going to move this point back. I'm going to sample points on this half sphere and do that everywhere. And we get the boundary between stable and unstable helices. So the same scaling arguments we used to solve the manipulation problem allow us to compute this.
This had to be computed.
I have an analytical solution for the conjugate points that's implicit. So I have to find the zeros of that. I can't invert it. But all of the equilibrium equations and stability equations can be solved in closed form. So one thing you might notice here is we have these arms that jet out. It looks like they jet out to infinity. And in the equations, you have a term that keeps popping up. It's omega twisting rate minus 2 tau, twice the torsion. So if we plot a section here where omega is equal to 2 tau, this is what we get. So there's some oscillations at first, but then it dies down. So this is a nice result. This tells us if you give me a helical curve that's arbitrary torsion, no matter what torsion it is, that's fine, and a curvature less than 2 pi, then I can find a rod that traces, the center line traces that helix and is stable. You can always fit a rod to it that's stable. You'd think if you keep increasing torsion more and more and more, you're twisting it, it would eventually become unstable. We can make the torsion arbitrarily high if we want to. So now let's move on to surfaces. Here I have fewer results. This is something I'm just starting to think about. But this idea of scaling-based manipulation, we could extend it to two-dimensional surfaces that satisfy scale-invariant PDEs. So for example, let's take a simply connected surface. What I'm going to do is simply connect it so I can take the boundary and contract it down to a point. As we're contracting it, I'm going to take whatever's in the interior here and rescale it. And I'm going to rescale it in this case so that the length of the boundary always stays the same. Kind of like our rod videos from earlier. We're scaling down. Here we're actually going all the way to, so it's flat. And I pick a new shape, and I rebend into that.
Is this pure geometry, or is there some mechanics going on here?
This is just geometry. I'm just taking the surface and scaling it to show what happens. But the question we could ask relates to soap bubbles. So the partial differential equations that govern the shape of the soap bubble are scale invariant. So it seems reasonable to ask, is the set of all simply connected and stable minimal surfaces path connected? Can I apply that scaling procedure we saw on the previous slide to a soap bubble to flatten it and rebend it into some other shape? That's something I'm looking into. I don't have a good answer. I don't know very much about minimal surfaces, so maybe this is known, maybe not. I think it's an interesting question. So, takeaway points from this were that scaling symmetries allow us to do a few things. Allow us to show that the set of stable and collision-free equilibrium configurations of the rod is path connected. It allowed us to compute the set of stable helical equilibria of the rod. And it allows us to start thinking about deformable surfaces, how we should manipulate those. So that's the end of the research portion of my talk. There was one other thing that I kind of wanted to advertise. So when I was in grad school at Illinois, I worked for about 5 years with a program called EJP, the Education Justice Project. We taught junior and senior level courses to students who were incarcerated in Danville, Illinois. And what I did with EJP was I coordinated the computer lab. I started my second year of grad school. And when I first started, there was a group of about 5 guys who were really into learning Python. They were just starting up. They were really enthusiastic. And over the next 5 years, they spent a lot of time learning how to code. And the last semester I was there, we did a workshop on machine learning. And we actually built a neural network and trained it on the MNIST handwritten digit set, which is pretty cool if you think about doing that in the prison without internet access. These same guys also developed their own curriculum for an Intro to Python course and taught it to other students who were incarcerated, who were just learning computer programming for the first time. So there's a nice video, if you search EJP video documentary, pull in your heart a little bit. But the reason I'm talking about this is because there's a similar program here called the Cornell Prison Education Program, and we just built 2 computer labs. One is at the Cayuga Correctional Facility in Portland. The other one is in the Auburn Correctional Facility in Auburn, New York. These are just starting out now. One was built in October, one was just built last week. But I'm hoping that we can develop these into something like we had at Illinois, where we have a group of students who are really into programming, want to do things like machine learning and graphics. So if that interests you at all, I'd be happy to talk about that. I'm trying to recruit people, since we're just starting out, to come out and staff the computer lab, help us teach coding eventually, something we're working towards. So even if you're not interested in volunteering with this, but you want to ask some questions, I'd be happy to talk about that as well. So thanks for coming out today in the cold, and I'll take any questions.
Well, we have time for a few questions.
Yeah.
Hi. You've shown that for the elastic rod case that you always can connect from, your space is nice enough that you can connect from one point to another. But kind of heuristically, how nice is the topology of your admissible solution space? Like, are all the inadmissible solutions off in a corner, or are there just like holes everywhere and your paths are just super tortuous?
Yeah, I haven't been able to say anything analytically. Well, the one thing we have from this path connectedness result is that the space is kind of star-shaped. I say kind of because these aren't straight lines, they're curves that come back to the origin. But it's star-shaped with respect to the origin in some sense. The origin can see everything. Does that make sense?
Yeah, so everything around the origin is kind of nice,
so,
and then once you go out.
So that's the question, how far back do you have to scale before you know you're stable? Is there a ball around the origin? In the planar case, we know there is. The ball of radius 2 pi is always, everything inside that is always stable. I think that extends to the 3D case. All the numerical evidence I have suggests that. Another way to motivate that is that you can take the equilibrium equations and solve them in terms of an elliptic function. The period of that elliptic function, it's longer than the length of the rod if your initial condition is within that ball. That numerically seems to suggest that you're always stable. That's something I'm still trying to prove. But there is a ball around the origin that's stable. It's just a question of how big it is.
Oh, okay.
Yeah.
I'd like 2 small questions. The first one was when you had this assumption intrinsically straight. I was wondering what that meant.
So that means that the natural shape is straight. So this is pretty much intrinsically straight. Something that has a natural shape, so there's no forces acting on it, maybe it's a U shape. That's not intrinsically straight.
And this is under no external forces, like gravity or...
Right, so no external forces, no applied forces at the end. We're looking at what the natural shape is that takes, and nothing is acting on it. That's the intrinsic shape.
Have you been able to think at all about how adding in extrinsic forces, external forces would?
Yeah, so the result about the configuration space being a 6-dimensional manifold, that is preserved if we add external forces. So we can have gravity. The one thing gravity does is it breaks the scaling symmetry, right? So the idea I've been thinking about there is we have this configuration space that's path connected. What if we augmented that with another axis, and now we're in a 4-dimensional space, if we're in the planar case. And that extra axis is gravity. So when there's no gravity, that's like the level slice where gravity is 0. We want to lift that up to whatever value of gravity we're interested in. We're trying to show that those 2 spaces are diffeomorphic. So there's some results from a field called Morse theory that I think might be helpful there for showing that those 2 level sets are diffeomorphic.
The other, sorry, I guess this is The other question I had, I was wondering, because I was thinking about things with like, I don't know, that are easily bent or something. Are there external
Plastic
forces?
deformation or?
Yeah.
Okay.
And I was just, I was wondering if this is all in equilibrium. I was wondering how, if you're doing this in the real world, if there's a sense of how the dynamics actually come into play.
So, I
In
think
terms
there's
of like,
one question about plastic deformation, one about dynamics, or both together.
yeah, I guess I was interested in how if there's a sense of when you're moving these grippers around, how the dynamics might come into play in terms of some
Yes,
of these.
thanks. That's an interesting question. If you plan a path quasi-statically, you can ask, how fast can I execute that
Exactly.
and still wind up in my goal shape? Right. So I've seen some work in that on systems of ODEs. So how fast can you move this fixed point and it still settle down at the end to that fixed point? But this, if you're doing this dynamically, this would be a PDE. I haven't seen a whole lot there. And so I think most of the work would have to be computational, it seems like to me at least. I haven't done any of that. So it's an interesting question that I don't know.
I mean, but there's sort of general result that if you move slower than characteristic vibration times, you don't excite vibrations. So you kind of know the answer, right? You know what the natural frequencies are. If you're slower than that, you're safe, right? I mean, that's not
There's the natural frequencies of the configuration, you know,
Yeah.
and that varies as you move.
Yeah.
So you would have to take the minimum frequency, I guess, something like that. I don't know.
In the case of the helical rod, it seems to me there has to be a zero thickness for the rod. Otherwise, if you get intersections, you could have torsions and the like.
Yeah.
Is it? I'm thinking of winding a zero-length spring in particular, and I'm wondering, can you say anything useful?
So a rod, almost like a circular rod that laps over on itself.
Yeah, it touches and it's got force already built in just in its shape, in its original
Yes,
zero stress state.
There is, I've seen a paper where they include contact force.
Yes.
That prevents
Hey,
a
sure.
finite cross-section. And they get some stability results. It almost brings to mind a slinky, right? And I brought my slinky with
Just
me.
happening that way.
So something like this that winds around itself, but there's contact preventing it. It wants to be this length.
Right.
The contact
Exactly.
is being this length, yeah. So I should have known this would get pulled out. But
That slinky will travel.
so I could have given, if I can get to it, an entire talk on slinkies, and all the bifurcations they can go through. So it's something interesting that I've been thinking about. In terms of helical stability, I haven't thought much about that, how this pretension affects stability. And pretension gets so large that it becomes unstable. I don't know, that's an interesting question.
This slinky is a one-dimensional continuum with no coils in it, is that correct?
So I am modeling it by the center line.
And just a zero rest length.
Yeah, so this is the rest point here.
So it's got all kinds of weird linear differential equations starting in it. This is the zero rest length assumption.
Right, but I'm also modeling the contact between the coils.
Oh, you have
Keep
the
it-
contact.
I have
That's a
contact.
hard constraint.
Yeah.
For these surfaces, the scale and variance surfaces, what's the sort of equivalent? You have, robotic. What is the equivalent hold on the surface? Like, how are you deforming the surface? And have you thought about that yet, or is that still?
Yeah, so in the minimal surface case, you would need to be able to actuate, in theory, actuate every point along the surface. I don't really know how you would do that, so you would approximate it by manipulating many different points along the surface. I've also been thinking about elastic strips. So if you're holding two ends, but the two other long edges are free, manipulating that. If you're actually doing a full plate, then you do have to worry about how you're holding the ends. Are you holding it straight, or which edges are free? So it gets a lot more complicated when you go to a plate theory.
Like a soap bubble doesn't necessarily have some specific spot it's being held at, it's being formed.
So here I'm assuming that the end, or the edges, I can specify their location in space. So imagine I take a string, dip it in a soap bubble, and the robot is able to deform the string into any arbitrary shape. We're looking at what the soap bubble does.
Okay.
So again, I don't know how you would do that. I guess you have to approximate it with many little robotic grippers that can do something like that.
Okay, well, we have some refreshments next door. Let's thank Andy again.